All right, good morning, everyone. Thank you for taking the time out of your busy schedules to join us today. I'm Mike Albertson, Deputy Director here at the Center for Global Security Research. And it's my great pleasure today to welcome back Dr. Philip Duffy, the President and Executive Director of the Woodwell Climate Research Center. As many of you dialing in are likely aware, at the urging of former lab director Michael May, in early January, CGSR conducted a 3-day workshop on the topic of the security impacts of climate change, which generated a great deal of discussion and feedback and a clear signal that the center needed to do more to bring together various communities of interest on the topic. The final report of that workshop is posted on the CGSR publications page, and I will go ahead and send the link around here in the chat function to those interested in reading the findings. Also available for those who are interested is the annotated bibliography from that workshop, which has a lot of good reading material in there for those wanting to learn more on the subject. And again, I'll send that out in the chat function as well here when I'm done speaking. From the feedback we received on that workshop, one thing we decided to do sort of immediately was to start hosting speakers on this subject at least once a quarter, in the hopes that that would help set the stage for a follow-on workshop in early 2022 on the subject. Dr. Duffy was one of the standout panelists from the January workshop. He presented on the subject of managing climate change and strategic rivalry. He brings a wealth of public and private sector experience to the topic. He's a frequent commentator in the media and provides a real sense of needed urgency to the debate. I was reading a Washington Post article from a few weeks ago where he was quoted as saying, "Globally, we're not in a great place." So I hope today we can get to a slightly better place through both listening to him and the interaction afterwards. A brief reminder on protocol. Dr. Duffy will speak here for about 45 minutes, at which point we'll open up to questions and answers. Please submit your questions electronically to myself or Katie Thomas. And anytime during the presentation, the earlier the better, as we start getting the queue together. You can also raise your hand electronically. If you do raise your hand, be sure to sort of stand at the ready to jump in when you're called on so we can get as many people in the conversation as possible in the time we have available. So Dr. Duffy, thank you again so much for joining us and sort of kicking off the speaker series on the subject, and I'll turn it over to you now.
Phil, you're muted.
Thank you, and thanks so much for having me. And it's a great pleasure to be here. I'll just say I only wish that I could do this event in person. As some of you know, I spent a majority of my career working at Livermore, and it would be wonderful to have the opportunity to reunite with some old friends and colleagues. But like a lot of other things, that's going to have to wait, I guess, until after the pandemic. So I'm going to share my screen. This worked 5 minutes ago. We'll see if it still works. And what I'm going to do today is take a slightly different tack from what I discussed in the workshop that Mike mentioned, and I'm going to address a question that comes up with surprising frequency, and that is why do we still need climate science? Well, before I do that, I'll spend a few minutes and introduce the organization I work for, Woodwell Climate Research Center. You may know us by our former name, Woodwell Research Center. We were founded under that name in 1985. We're a global change research center. Superficially, well, we're an independent entity. We're a nonprofit entity. I would say superficially, we look a lot like a university research department. But a couple of things we do that I think are quite different is we focus our work on problems having immediate societal relevance. I mean, we're really about informing societal decisions and societal policies relevant to climate change. And one thing that I think characterizes and distinguishes our work is our approach of working with decision makers throughout the research process. And I'll show some examples of some of the decision makers we work with, but the approach is that we actually work with them to design the research agenda, and we collaborate with them throughout the research process And what that accomplishes is then at the end of the research process, we're confident that they're getting what they want, what they need, and we get the satisfaction of knowing that our work is put to use in the real world. And as that suggests, a big part of our approach to real world impact is through working with partnerships. And these are some of the partners we work with. And I'll again emphasize, these are not scientific collaborators in the normal sense, but rather entities who use our science in the work that they do every day. And historically, we've worked with governments at all levels around the world. We've also worked with large conservation organizations. More recently, we've started working with leaders in the world of business and finance, and some of those folks are listed up top. And we in particular, for the last several years, we've worked with a large coalition of asset managers led by Wellington Management, also including the California Public Employees Retirement System, Ontario Teachers Pension Plan, and a large sovereign wealth fund. We're also starting to work with folks in the insurance industry, and all of these, what these have in common is they're starting to come to grips with climate change as a near-term risk. So the question I get asked sometimes is, why do we still need climate science? And I've even had folks ask me, how does it feel to have your profession be rendered unnecessary? And I'll say I certainly don't feel that my profession is unnecessary. In fact, I feel like there's more demand than there ever has been for climate science. And actually, one of the things that's happened just in the last couple of years, which is quite remarkable, is that some forms of climate data anyway now have financial value in the marketplace. And as you may know, there are, in fact, for-profit firms springing up in Silicon Valley and elsewhere, which provide climate risk information to paying customers. But this is actually, in some sense, not an unreasonable question. And the basis of the question is as follows, right? And I'm going to show you here covers of reports of the Intergovernmental Panel on Climate Change, the United Nations scientific body, and these reports come out every 6 or 7 years, and these are the 4 most recent reports, and every one of them has some sort of a summary statement about human causation of climate change. And the first one of these goes back to 1995. The last was issued in 2013. And what you see is these summary statements have gotten stronger over time and more quantitative, and as a result, they've gotten longer. And so the font size here decreases from left to right. And I'll say two things about this. One is I just call out that the 1995 report, that chapter that contained that statement, was the lead author was a good friend of mine from Livermore, Ben Santer. But the larger message here is that human causation of climate change is simply beyond doubt. And the science, in fact, says that not only is there no doubt that humans are causing climate change, but in fact, our best guess is that if you look at global temperature increases over the last 50, 60, 70 years, essentially all of that is attributable to human activities, and very little of it, in terms of that multi-decadal trend, is attributable to natural factors. So humans are causing climate change. We also know that one thing we need to do, probably the main thing we need to do to address that, is to stop adding greenhouse gases to the atmosphere. And this is showing the sectors where the sectors of the economy, rather, where greenhouse gas emissions come from. So we know that humans are causing climate change. We know we need to stop these greenhouse gas emissions. And so that does raise the question, well then, given that we know that, and furthermore, given that we're actually not doing much in terms of reducing these greenhouse gas emissions, why do we still need climate science? And my answer to that is actually pretty simple, and that is that we need climate science to inform policies and decisions, which we need to help manage the issue of climate change. And a couple things. I mean, one is I'll say I use the word manage climate change rather than solve climate change because it's not an issue we're going to solve. It's not going to go away. We can halt its progress and we can cope with the consequences. And another point I'll add is just that we've all seen over the last year how important it is to have science-based policies. And I'm thinking of COVID, right? I think COVID gave us a vivid reminder of, well, that policies based on science work. Policies based on wishful thinking really don't work. So we need climate science to help inform climate policies. And I've broken down the policies we need into 4 categories. And the first of those is what we call in the business climate mitigation. And that means essentially reducing the drivers of climate change, which means reducing the amount, in large part means reducing the amount of greenhouse gases in the atmosphere. And as I'll explain, that nowadays also includes CO2 removal, removing carbon dioxide in particular from the atmosphere. So we need policies on mitigation. We need policies on what we call adaptation, and that means essentially coping with the consequences of climate change, which, as you all know, we're experiencing right now. And again, those aren't going to go away. In fact, they're going to get worse as the climate continues to warm. And so we need climate science to help us understand exactly what it is that we need to develop plans to manage. I'll mention 2 other policy elements that we need science to inform, and one is so-called geoengineering. And this term refers to the idea of counteracting some of the effects, not all, but some of the effects of increasing greenhouse gases by reflecting a little bit more sunlight back out into space. I'll talk about this more, all of these actually more in a minute. I mean, this is an idea that everybody loves to hate. My view is that it needs to be on the table. It needs to be something that we at least understand better so that we can decide if it wants to be part of the toolkit or not. And finally, I'll mention measurement of national greenhouse gas emissions. And as you know, in 2015, every country in the world signed up to a climate agreement, the Paris Agreement, and this is aimed at having countries reduce their emissions of greenhouse gases to the atmosphere. One of the limitations of the Paris Agreement is that it is based on self-reported emissions. In other words, one of the stipulations in the agreement is that every country every 2 years has to measure and report their own national greenhouse gas emissions. It's, I think, a significant weakness of the agreement that at present we have very little means to independently measure anyone else's greenhouse gas emissions. So I won't name names, but you can imagine countries where it's reasonable to question, are the emissions which they're self-reporting, how accurate are those? It would be nice to have the ability to measure that independently using science. And as I'll show you, I think there's certainly prospect for doing that. So, okay, my screen's not advancing. So I'm going to just expand on all those areas a little bit. And before I do that, I'll just say, the question I'm addressing is why do we still need climate science? And before I answer that, I'll just answer the question, what do I actually mean by climate science? And as you'll see, I'm taking a somewhat expansive definition of that term. And I'm defining here climate science as science which is related to some aspect of the Earth system, which informs policies or decisions needed to manage climate change. So for example, well, this includes things which you might not necessarily think of as climate science, so I'll show you in a few minutes. One of the things we're working on is technologies to accurately and cheaply measure the carbon content of soils, because that can be an important tool in climate mitigation. It does not include aspects of science, for example, better batteries, which are very important, but which are not related to the Earth system itself. So again, this is my working definition of what I mean by climate science. So let's talk about climate mitigation and the science we need to inform mitigation policies. And I'm going to start with this, and this is from a recent report of the Intergovernmental Panel on Climate Change. This is, well, this was issued in 2018, and there's a bunch of curves here, and these are all trajectories of global greenhouse gas emissions going forward, and these trajectories share the property that they all limit the global temperature increase to 1.5 degrees Celsius, which is a target we think might result in a livable world. There's multiple trajectories because there's multiple ways to meet that goal. These all share the property, these emissions trajectories all share the property that they start with very rapid reductions in greenhouse gas emissions. And if you can see the scale here, you'll see that these trajectories pass through zero around 2050, plus or minus a decade or so, meaning that towards the end of the century, these scenarios call for substantial negative emissions. And what that means is simply that these scenarios call for humanity to remove more carbon from the atmosphere than we add to it. And this is something which we don't know how to do at the scale called for here. And so this is a scientific and technological challenge, and it's partly a climate science challenge, as I'll show you, and partly an engineering and technological challenge. Where this intersects, where the need to do carbon dioxide removal intersects climate science, is through the so-called natural climate solutions. And the term natural climate solutions refers to the idea of managing land in ways which act to remove carbon dioxide from the atmosphere. And one of those is reforestation. I'll explain the map here. Well, I'll explain the map in a minute, right now actually, and then talk about some of the implications. So what is this map showing you? I'm calling this unrealized carbon storage in forests. And so what it represents is the potential to add more carbon to forests through letting forests regrow. And so what it starts with an estimate, a point-by-point estimate of the biophysical potential for carbon storage. How much carbon could be stored in forests everywhere if we simply let them grow to their maximum size? And then from that estimate of maximum potential storage, we subtract a measurement, a satellite-based measurement of how much carbon is in fact stored in forests now. And the difference represents the potential to add more carbon to forests. Now, if you add all of this up, so this shows you where there's potential to add carbon, and you can see northwestern U.S., the tropical forests, Amazon, Congo Basin, Southeast Asia stand out. If you add all of this up, the potential, theoretical potential, is quite substantial, of course. And I'll say that we've masked out regions where you're obviously not going to do reforestation, like cities and also areas which are now under cultivation. Even so, one is obviously never going to come close to realizing this theoretical potential, but nonetheless, if you add it all up, it's very substantial. It's not enough. We certainly need technological carbon dioxide removal, but what this work shows is that there is in fact a lot of potential to help remove carbon from the atmosphere through reforestation. The same is true actually of restoring carbon to agricultural soils, and that's what this map shows. And we refer to this as soil carbon debt. And what this is showing is estimates of the cumulative loss of carbon from agricultural soils, cumulative since the beginning of agriculture 8 or 10,000 years ago. And you can see, again, well, it says here that the total of this summed over the whole planet is quite large. It's equivalent to something like 13 years of global CO2 emissions. So again, this potential is theoretically very large. Obviously, one is not going to realize anything close to that theoretical potential, but even if one realizes a fraction of it, it's very, very significant in terms of what we need to do to help manage climate change. And so some of our work at Woodwell involves, well, first of all, we make maps like this, and we can use these maps to inform policies and projects on a regional scale and local scale. We also work on something I mentioned earlier, which is inexpensive measurements of soil carbon. And there's an enormous interest now, including interest in the private sector, in restoring carbon in agricultural soils. And one of the challenges is it's very, very difficult and expensive to measure carbon, soil carbon. And if you can't measure it, obviously, then you can't be sure that you're managing it well. And you can't be sure that you are, in fact, restoring carbon to agricultural soils if you think you are. And so we're working on spectroscopic methods which involve small handheld spectrometers, which can, with proper modeling and so forth, can actually tell you a lot of soil properties, including estimates of the carbon content. And this work that we do on the so-called natural climate solutions has contributed to decarbonization plans for the country of Poland and also for the EU. And these were actually carried out by, well, folks we work with at McKinsey and Company. And these decarbonization plans focus primarily on the energy sector, which is not our area of expertise, but in order to reach net zero, because certain sectors of the economy are very difficult to decarbonize, it's really important to take advantage of land sinks of carbon and maximize those land sinks. And this is where we've been able to contribute to these sorts of efforts. So those are some of the issues associated with climate mitigation policy, but there's other issues as well, which I think are of a more fundamental and profound nature. And one of these questions I frame as how much climate change is okay. In other words, the policy community is focused on limiting warming to 1.5 or 2 degrees Celsius. That's above the sort of baseline temperature, which we refer to as a pre-industrial temperature. But the fact is, we know relatively little about what the world actually looks like at 1 or 2 at 1.5 or 2 degrees Celsius. And my view is that we need a lot more science to help us understand, well, the physical consequences of that much warming and also the socioeconomic consequences of that much warming. In other words, we need to understand at what point the impacts of climate change really become intolerable. And we need to develop a better understanding of what, in fact, is at risk. And to me, things like the wildfires which we experienced here last summer really drive home the point that, well, the consequences of climate change, certainly regionally, will become very, very significant at 1.5 or 2 degrees of warming. And here's an example, and this is a map of drought in the 2040 to 2049 decade. You can see this is the Mediterranean region. This is changes in drought, well, middle of this century relative to middle of the last century, roughly speaking. And we've used here a measure of drought called Palmer Drought Severity Index. It's a very commonly used measure of drought, and it's sensitive to both temperature and precipitation. It's in some sense a measure of soil moisture, and soil moisture is a useful measure of, well, it's a useful proxy for wildfire risk. It's also very useful for thinking about agricultural impacts. And what this shows is that the Mediterranean region is going to get very much clobbered by drought in the next several decades. And the units here are a bit obscure, so I'll just kind of walk you through. What we're showing is the difference between the future period and the so-called reference period, the difference in the number of 3-month droughts per decade. And a 3-month drought here again is defined as Palmer drought severity index less than, I think, -4, which is a severe drought. And what this is saying is that, so where the darkest shades are, it's saying that there will be more than 20 additional 3-month droughts. So 23-month droughts means an additional 60 months in drought per decade. Well, 60 months is 5 years. So this is saying in these darkly shaded regions, these regions will be in drought and severe drought most of the time in the middle of the century. And this results from a combination of both reductions in precipitation and also warming, which contributes to soil drying. And as I mentioned, that particular index of drought is useful for thinking about agricultural impacts. And I'm not going to, I guess, walk you through all these numbers, but one thing we've looked at, which is interesting, is the likelihood of simultaneous crop failures in major bread baskets around the world for 4 commodity crops, maize, wheat, rice, and soybean. And what this analysis shows is that as the world warms, the likelihood of these simultaneous crop failures increases, and obviously this can affect food prices, food scarcity. It could also be a trigger for conflict and political instability. And here's another example of near-term risk, and this is a measure of extreme heat, and I'm going to show you in a minute how we've translated this, started to translate this into some socioeconomic consequences. This is a measure of extreme heat. It's looking at number of days per year where the so-called National Weather Service heat index enters what's called the danger zone. The heat index is a measure of extreme heat, which is based on both temperature and humidity. And it's a useful index because the human physiological response to extreme heat depends on both on temperature and humidity. And this index was designed to capture that. And we're looking here at a part of the world that is already very warm, already very humid. It's very populous. It's an emerging economy. And what these results show is that the number of days per year when this heat index will enter the so-called danger zone is going to greatly increase over the next several decades. And this has socioeconomic implications, particularly in, say, India, which is a developing economy where outdoor labor is very important. Outdoor labor, for example, agriculture, for example, construction. And this, in fact, is an analysis of, it's an estimate of how much outdoor labor productivity will be lost due to increasing incidence of extreme heat. And this analysis was done by our colleagues at McKinsey & Company based on our modeling of the physical risk. And again, the message is that just in the next several decades, there will be significant outdoor labor productivity loss in this important emerging economy. And this is an example of a fair bit of work actually we've done with McKinsey & Company over the last several years of looking at some of the socioeconomic consequences of climate change. And again, my view is that this work is really important because it really helps to illustrate what is at stake. And that allows us to make more informed decisions about is 1.5 degrees really the right target? Or is 2 degrees the right target? Or what is the right top line target for global climate policy? So that's one of 2 mitigation related questions, which I think are of a fairly fundamental nature. The other has to do with the stability of climate at 1.5 or 2 degrees. And let me just explain what I mean by that. and that is that climate policy is based on an assumption that if humanity stops emitting greenhouse gases totally, that the climate will stabilize soon, and in fact will eventually, not soon, but eventually start to cool. But is that really right? And the reason that might not really be right is that we know that in a warming planet, there are sources, well, certain biotic sources start to emit greenhouse gases, which introduce a warming tendency. And the most important of those almost certainly is permafrost. And this is a map of, well, it's a map of the world looking down, northern hemisphere looking down on the North Pole, not the normal perspective. And the shaded areas show areas which are covered by so-called permafrost, and something like 25%, 24% of northern hemisphere land area is now permafrost. And what is permafrost? Permafrost is perennially frozen ground, and the name permafrost suggests that it's permanently frozen. But of course, what's happening is the Arctic, the northern regions are warming very, very quickly, and permafrost is starting to thaw. And we know that, well, there's no question about that. I mean, you've probably seen pictures like this. This is a road that was built on ground that used to be frozen, is not now frozen. There's all kinds of regional consequences, excuse me, from thawing permafrost, consequences for this sort of infrastructure. But there are global consequences as well. And the global consequences have to do with greenhouse gas emissions. And as permafrost thaws, permafrost consists of organic matter, which has been frozen, which hasn't decomposed, and much of it's been frozen for tens of thousands of years. As it starts to decompose, like anything, it emits gases, and some of those gases are greenhouse gases, which contribute to global climate change. They contribute to warming, and we're one of the first groups to actually measure greenhouse gas emissions from thawing permafrost, and they're clearly significant. And this is a paper that we published in Nature Climate Change, well, a year and a half ago, actually showing that even in the winter season in the Arctic, that emissions, greenhouse gas emissions from permafrost are significant. So again, the point of this is that this is happening now at a global temperature of about 1 or 1.1 degrees above baseline. If we allow the planet to warm to 1.5 or 2 degrees, obviously these more permafrost is going to thaw, these emissions will only increase. And again, that introduces a warming tendency, and it raises the question, well, will the climate even be stable, or will it continue to warm on its own after humans stop adding greenhouse gases to the atmosphere? And I want to point out that we don't know that that's true. This is clearly a warming tendency, but there are also cooling tendencies. And first and second among those are the land carbon sink and the ocean carbon sink, which are very significant. And it's not clear who wins. So I'm not saying that, I'm not trying to be catastrophic here and say that we're doomed to an indefinitely warming planet. But it's certainly a risk. And again, just to be clear about it, the risk is that thawing permafrost contributes greenhouse gases, which cause more warming, which cause more permafrost thaw, and so on and so on. So this does tend to be a self-reinforcing cycle. Okay, that's a lot about adaptation. I'm going to move more quickly now and talk about, that's a lot about mitigation. I'm going to move more quickly, talk about adaptation, talk about geoengineering, talk about measuring greenhouse gas emissions. Adaptation, again, is the process of coping with climate change. And what science can do here is help folks to understand what, on a very quantitative and granular level, what risks they face. And so we can help prepare for them. And here's an example. This is a map of flood risk. This is Boston, God love it. And this is actually, in fact, not even a map of future flood risk. This is a map of present day flood risk. This is a 1 in 100 year event. And you can see there's a lot of flood risk in Boston, and many of us are baffled. I showed this slide originally at a talk in the Boston Convention Center, which is highlighted here on the map, and you can see that that's an area subject to significant flood risk. The Seaport District, which is just above the convention center there, is an area of very, very rapid construction and development right now. And you can see from this that there's major flood risk even now in that part of the city. And many of us are baffled at the amount of investment that's going into this very, very at-risk area. And so, again, this is an example of how science can help, ideally would help inform decisions like where to develop and where not to develop. And I guess this is an example where that process hasn't worked very well. Here's another. This is a map of Australia showing an increase. Well, it's essentially showing increases in fire risk, and the specific metric here is projected increases in the number of high fire risk days in looking forward a couple of decades. And we've shown also here in the dark gray where the fires were in the last couple of years, and we've also shown here represented as topography. We've shown here vegetation, and because obviously for the fire risk to be realized, there has to be vegetation. And having this kind of information, again, on a very granular level, can be helpful in informing decisions about, well, where to build, where not to build, and what sort of policies we want to help manage these risks. And I should say, and I'll summarize this at the end, that there's a lot we need to learn in the research community about how to model these risks better. And in particular, well, fire risk is one that's obviously a very, very rapidly evolving risk. And I'd be the first to tell you that this model is not predicting the level of risk. And I don't think anybody's model of wildfire risk is predicting the level of risk which we're already experiencing. And again, I'll summarize at the end some of the things I think the research community needs to work on to do better at producing the science that we need to help understand these risks. And I'll turn now to geoengineering, which I mentioned earlier. And this is sometimes thought of as a last resort climate strategy. But again, the idea is to counteract some of the consequences of increasing greenhouse gases by reflecting more sunlight back out into space. And we have a lot of confidence that this would work because nature provides an analog for one form anyway of geoengineering through large volcanic eruptions. And this is, on the left, this is a picture of Mount Pinatubo eruption in 1991. And the panel on the right shows that that volcanic eruption, because it added a lot of particulate matter to the stratosphere, actually had a measurable impact on the global temperature. And the two curves there, one is an observed temperature record and one is a model, and I forget which is which. It doesn't really matter. The message is that in adding particulate matter to the stratosphere has a significant cooling impact. It's not very long lasting, but again, it is significant. And one of the thoughts for how we might geoengineer the climate is to deliberately introduce small particles into the stratosphere. And as I said, this is not, this is an idea that I don't think anybody loves. A lot of people hate, but my view is that we need to understand it better. And specifically, we need to understand how well it works. We need to understand effectiveness. We need to understand unintended consequences, which there will be, but right now we don't really know what they are. And we also need to think about issues of governance. And by governance, I mean questions like, who makes the decision to do this? And this is, some forms of geoengineering, many of them are something that could be done by a single nation acting alone. So who makes the decision to do it? Who makes the decision to stop it? How do we handle the inequities generated by the consequences of geoengineering, and so forth? So a lot we need to think about and study here. Okay, and finally, I'll just return to the subject of measurement of national greenhouse gas emissions. And as I said, the Paris Climate Agreement is based on self-reported emissions, and these are estimates of national emissions. These are actually, I think, only energy sector emissions, not land use emissions from different nations in the world. And the question is, how well do we really know these numbers? And obviously, for any climate agreement to really have teeth, we would need something stronger than self-reported emissions. And science can help us with that. And there are, in fact, folks working on this. But the thinking is that essentially by looking at relatively small inhomogeneities, relatively small variations in the concentration of CO2 in the atmosphere, and here's a map of that on the right, measuring those concentrations and using so-called inverse modeling, which starts with the concentrations and tries to infer sources. With enough data, with enough modeling, and data would include satellite data and in-situ data, with enough data and enough modeling, one can make some science-based estimates of national greenhouse gas emissions, and something like this would go a long way to giving us more confidence in nationally reported greenhouse gas emissions. So this is a big challenge, but again, there's folks working on it, and it's, I think, pretty clear that a lot of progress can be made. Okay, so I'll conclude with just some thoughts on challenges for the climate modeling community, and I'm focusing on the climate modeling community because that's, well, partly because that's a community that I was part of for a long time, and also the climate folks at Livermore are very much part of that community. And there's a lot of work we need to do to get better at providing the sort of information that policymakers need. And I have a list of a few things here. And first on that list is we need to do a lot better at simulating climate on local and regional scales. And of course, the local and regional scales are where the impacts are felt. And the local and regional scales are where a lot of decisions and policies are made. And right now, we're actually not very good at simulating local and regional climate. There's some real technical challenges there. Related to that is we need to get better at simulating climate and weather extremes, things like tropical cyclones and so forth. These things have, obviously, these extremes have disproportionate societal impact, and yet they're actually an area of weakness in our models right now. And furthermore, there are a lot of phenomena which have a lot of societal impact, which aren't included in climate models at all. And the two examples which stand out are wildfire and flood risk. And so when we simulate those, we use information from climate models to drive specialized models which focus specifically on those perils. But we need those again are things that we're not, well, wildfire in particular, as I've said, we're not very good at simulating right now. And we really need to work on getting a lot better at that. And finally on this list, I'll mention carbon cycle feedbacks, and this refers back to the idea. Well, I gave the example of greenhouse gas emissions from thawing permafrost, and this raises the possibility that, well, it does raise the possibility that we could, it's conceivable that we could lose control of our own destiny if biotic sources like permafrost really started to emit carbon in a major way. I don't want to be overly alarmist. I don't think that's, well, it's certainly not going to happen soon, but it is, I think, a risk that we need to think about. So that's one thing. Another issue which is of great personal interest to me is the modeling community is doing a lot of work on this, but we have a lot more to do, and that is just quantifying uncertainties. And decision makers tend to want to know about uncertainty, and we're not. Obviously reducing uncertainty would be great, but even if we could just quantify it better, that would be a step forward. And I'll say though, this is very important. I will say I think that sometimes the research community gets overly focused on that, And I'll mention, I'll just say that in the work that we're doing, that I'm involved in now, that my organization is involved in now with decision makers, in a lot of instances, we're really, in some sense, harvesting low-hanging fruit. And I'm thinking of the work we're doing with the financial industry. And these are folks who have never before thought about climate change and physical risk from climate change as an investment risk. They've never thought about it at all, okay? And what this means is that information which is pretty uncertain can actually be useful to them. And as I think I said in the talk I gave at the workshop a few months ago, none of the decisions that these folks are making depends on the third significant digit of the results that we're giving them. Information that is directionally correct, that has the broad geographic distributions mapped correctly, in many cases can be very useful to decision makers today. I mentioned two more things and then I'll close. And then as I think the research community is struggling and needs to do more to work with other communities. And as I've said, I think it's really important to do better at understanding the human dimensions of climate change. It's the socioeconomic consequences. And to do that, those of us in the physical science community need to learn to work more effectively with social scientists. And there's a lot of barriers to doing that. There's institutional barriers, and cross-disciplinary research, excuse me, is always very challenging. But I think this is something that's extremely important. And similarly, we need to get better at working with stakeholders, like city managers, for example, to help them understand the risks that are coming and to develop strategies to manage those risks. And again, there's some scientific challenges to doing that, which I've outlined here, but there's also some institutional challenges. And for example, in academia, it's, I think, difficult to get tenure by making a career out of helping small cities cope with flood risk, for example. So to summarize, I think climate science is in more demand now than ever before, and it's actually, for those of us who've been in the business for quite some time, I guess we knew this day was coming, but after a while you start to ask yourself, is it ever really going to arrive? And in fact, it's here. So I'll thank you for your time, and I'd be happy to address any questions.